Hello, doctor. My name is Usman Abdulrahman Shehu. My matric number is AE220098. And my friend here, his name is Megan Nadarason. We are in Group 1, Section 5. Firstly, I'm here to present about the introduction. Introduction. Fourier series is a mathematical representation that decomposes a periodic function into a sum of sinusoidal components. It allows us to express a periodic signal as an infinite sum of harmoniously related sinusoid functions, that is the sine and the cosine. The components of the Fourier series are called harmonics, and they have different frequencies and amplitudes. This project involves working with MATLAB to perform Fourier series analysis, analyze signals in the time and frequency domains, design a low-pass filter, and investigate the effects of duty cycle variations. Secondly, the project utilizes previous developed code from Project 1 and 2, pre-Project 1 and 2, by reconstructing signals in the time domain and analyzing their frequency components. Thirdly, insights into the signal characteristics are gained. A low-pass filter is designed based on the given specifications and its output is analyzed in both time and frequency domains. To validate the analysis, a circuit reference of the filter is constructed and compared with MATLAB simulations. Varying duty cycles are investigated. Unsuitable resistors and capacitors value are determined to construct a circuit, which is then simulated to validate the earlier analysis of the project report presents the finding and discussion regarding the records obtained.
Thank you, Osman, for the introduction that you've given for our group. So let's get into the work directly without any delay. So this would be the assignment question for this subject, and I would like to remind you guys that before getting into question one, the frequency that we were given is the FO is 100 kilohertz and FC is 600 kilohertz. This is because we are like group one from group one, so this is the our designated frequencies. So without any delay, let's get into the question one and two. So for question one and two, we are asked to do a Fourier series analysis of the signal given, and we should plot the signals in time domain for 5, 10, and 20 harmonics. So we should analyze the signal both in time domain and frequency domain. And as already know, the period of the signal is already given by our lecturer, and then we should assume the duty cycle of the signal is 50%, which is tau equal to 0.5 t naught. So before getting into the software, I would like to show the calculation part of this manual calculation part of this question one and two. So this would be our calculation part, and we'll go deep into it later after getting into the software. So let me show you the codings for the question one and two. So these are the variables that have been given here on the top right here, which is d, n, t, t naught, tau, and x, xn, and xt. So let me give you a brief explanation about the codings out here. So as you know, tau is a variable, as I mentioned earlier, it's 0.5, and t naught is 1. And t equal to the ratio would be like -10, ratio 0.001, ratio 10. And the xt will be zeros, and xn will be zeros, 41, 1. So for n -20, ratio 20, which are the harmonics, there we were recorded there, the x0 size t, it initialized before the loop, as you all know. So first of all, we're going to do for the harmonics 5, 10, and 20. So the formula would be x equal to tau over t naught multiplied by sinc n multiplied tau over t naught. So this formula would be applied for all three harmonics out there, as you can see there. So the subplot and plot are just to plot in a diagram later. It will show to plot in coordinates out there to show the signals the signal to show you the signal. So as usual, the x would be the time t and y will be amplitude for all three. And then this is just the title of that all signals. So that's all. And then this here shows that variable of x. These are all the formulas to define the x. So x will be xn plus 21 and xt would be xt plus x power of exponent j multiplied by exponent j 2 pi n t not t. So I'm just gonna copy all of these and put in the command window. If I click enter, it will show you our output that we want. So after doing the Fourier series analysis, this would be our output. So as you can see here, this is for the harmonics 5, 10, and 20. And this is our impulse response of the Fourier analysis series. I hope that's quite of a good explanation for the question 1 and question 2. So let's dive into the question 3 out here. So question 3, we were instructed to construct a low pass filter using MATLAB with frequency response characteristic as given in figure 1a, which is the 100 kilohertz. For FO and FC is 600 kilohertz. FC is the cutoff frequency. So the gain formula for gain would be 20 log V out over V in. So let's get into the coding itself. Then the codings for the question 3 is out here. So as you know, the FO would be 100 kilohertz and FC would be 600 kilo. And W would be FO over FC over 2. So this is how it works. So W equals to W multiplied by FC over 2 pi. So and then we're going to plot this in a graph where W 20 log 10 and K. So the grid on is just to show the precise value of the signal out there. So let me copy and paste and show you the output for the question 3. So these are the two outputs that we would need for the question 3 out here. So this will be the output of the filter frequency response. And this is the filter frequency response without the logarithmic scale. As you can see, with the logarithmic, it's much more stable out there. So if you click it out here, you can see the precise value of the signal itself. And you can play around with it, and then we could see the value that we need at the specific time, the gains. Same goes here as well. So we could see the value of X and Y by dragging it off like this. This is all just to show you how to operate the MATLAB systems. So let's straight away get into the question 4. So question 4 it's a manual calculation part for the output of the filter both in time and frequency domain. As you can see here, we have completed the manual calculation and can be seen in more clearly in the report later. So question 5 is where we should construct a circuit representing the low pass filter. So we should pass our signal as the input to that filter, and we should analyze the output of the filter comparing its output with the simulation itself. So as you can see, the FC value, the formula for FC is 1 over 2 pi RC and FO is 1 over 2 pi R square root of 2C. So by using the simultaneous calculation, we would know that R is 1 kilo ohm and C is 0.6 nanofarad. So if you construct this circuit in the Multisim, which is another software, sorry that I couldn't able to show it right now because of some technical issues in my laptop as well. So if you create this circuit itself and then run it, you would get the gain out here, the response, without the logarithmic scale. If you notice, it's the same response as I showed in the MATLAB just now. It's almost same. So which means the task 5 is completed successfully. So let's dive into question 6 and 7 now. So question 6 is we should investigate the effects of having a lower or higher duty cycle. And we should set the duty cycle for the case of tau 10%, 20%, 30%, 70%, and 80%. And we should be able to identify the suitable values for both the resistance and capacitors. So, and we should construct the circuit and show that the analysis 456 is valid using the suitable simulation and software. And we're going to do it later. So as you can see, this is, so let me clear off this place for CLC, and then we're just gonna copy paste this entire thing. This is our, before that let me explain you guys. So this, on the top part here, it would be the continuous signal for the continuous signal codes for the continuous signal. So it is a 10% duty cycle, 20%, 30%, 70%, and 80%. As you can see here, these are our variables T, D, X. So T is the ratio of 0, 0.01, and 50, and D equal be 10. And then X will be the square of TD. And then if we plot everything, and it will calculate by itself later. So as you can go here, this part is the discrete signals, the output of discrete signals for 10%, 20%, 30%, 70%, and 80%. And for this, the N will be 0 ratio 0.550, and D could be 70, and X would be square ND. So if you put subplot for everything, 5 to 4 for the 20%, 5 to 6 for the 30%, 5 to 8 for the 70%, and 5 to 10 for the 80%. And then if we plot in a graph, we would get that our designated output. As you can see here, wait for a bit, since it's a lot of information out there, taking a little while. As you can see here, that's our duty cycle for the continuous signal and then discrete signal. Discrete signal, which means impulse response. So as usual, the Y will be amplitude, X will be the time. As you can see here, it is continuous according to its time, according to its duty cycle, and then the impulse response is these both are equal, and these both are equal. It's just that this continuous signal represented in a discrete form, which is an impulse form. And then I think that's all for now, because the conclusion part will be covered by my partner after this, and then this will be our minutes of meeting. And I hope that this I've elaborated everything quite properly. So thank you so much. And I would like to give a special mention to Mr. Dr. Ansar bin Jamil for guiding us throughout this time, and he has given us valuable advice that would be very insightful for our future. Thank you, Mr. Ansar. Thank you, everyone.
And secondly, I'm here to present about the conclusion. In conclusion, the Fourier series analysis, signal analysis in the time and frequency domains, construction of a low-pass filter, and simulation provide valuable insights and practical tools for understanding and processing signals. By decomposing signals into their harmonic components, we can analyze their frequency, content, and characteristics. The low filter allows us to selectively unweighted high-frequency components, while simulation validates the overall analysis. In overall, the combination of Fourier series analysis, signal analysis in time and frequency domains, low-pass filter construction, and simulation provides a comprehensive understanding of the given signals and their processing. And lastly, these techniques are valuable tools in signal processing and circuit design, and are allowing us to analyze and manipulate signals effectively for various applications. Thank you.